All right, so where were we? We learned some very cool logical combinators and or not, exclusive or. We made fancy truth tables, and then we got into binary. So let's go back to this slide. So binary is a number system. It's just another way of writing numbers. So we as humans, with our 10 fingers, we like decimal or base 10 numbers, where we can use 10 digits, 0 through 9, to make up our numbers. But binary is base 2. It only uses zeros and ones, and it's able to make up any number under the sun. So you only get 2 digits before you have to switch places. That's kind of interesting. And then binary digit, we don't like saying that too much, so people say bit instead. They just shortened it. And then a byte is an 8-bit number. And so we got lots of ones and zeros. And I have to use these subscripts to tell you which kind of base I'm talking about, because this is the number 2 in binary. This is the number 10 in decimal. So I have to say which base I'm talking about. Because 1 0 is not 1 0, meaning 10. Okay? So let's talk about how to convert. All right, let's take some numbers and convert them from binary to decimals. Like this number, it's not 10,010. What is it really? Binary to decimal. How do you do it? So the secret, the way that you're able to break this down and convert it to whatever it is in decimal, question mark, base 10, is you're going to do the thing that you kind of learned in elementary school to break down bases or break down places of numbers. So do you guys remember how, like, in grade school, you learned that 1,234, you could break it down as 1,000 plus 200 plus 30 plus 4, right? And eventually, once you got to maybe middle school, you learned, okay, I know powers of 10 now, so you can break that down further as like 1,000 is 1 times 10 cubed plus 2 times 10 squared plus 3 times 10 to the first plus 4 times, you can still have a 10 here, it's just got to be 10 to the 0. And do you see how you're breaking down this number into all of its places in terms of powers of your base? Ooh, that's going to generalize. All right, so that's going to work the same for binary, that kind of power expansion. So this number then, 10010 in binary, what is it in decimal? Let's just do this process and do the math. Instead of using 10, because our base isn't 10 anymore, we're going to use times 2 to the 3, 2 to the 2, okay? Usually you start with the rightmost digit. So like this digit right here is contributing how much? It's contributing 0 times 2 to the 0. That's the pattern. So that's the first digit. And then, all right, what's this one? What's this one doing? That's 1 times plus 1 times 2 to the first. So this is the 2's place in binary. That's kind of interesting. All right, plus 0 times 2 squared plus another 0 times 2 cubed. Those aren't very helpful, are they? Plus that one more right here. This 1 times the 2 to the 4th place, right? So this is the 16's place in binary. Interesting. So yeah, if you just break that down further, get rid of all the zeros. It's 16, 2, 4, 8, 16 plus 2. So that means this number, 10010 in binary, is secretly the decimal number 18. Are there any questions about that? Because that's going to be the trick to understanding binary. That's how we can bring it back to the number system that we know and love. All right? Are you good with that? All right, prove it to me. So here's my screenshot of that. Your turn. So let's see. You guys don't have to write this down anymore. Just like convince your neighbors that you're correct. But here, this is the largest 4-bit number, 1111 in binary. Do this kind of expansion. Figure out what it is in decimal. Right? Give it a try. You don't have to write it down. I'll just have a brave person shout it out in like a minute or two. But yeah, so let people help each other break down this binary number. What is 1111? The 2 in the zeros place. It's always the 1's place on the right. It's not 2 to the 1. The first power is 0. I think that's enough time to do the math. Any brave souls like to share the answer that they got? What is 1111? Oh, we're not very talkative today. I will have to fix that later. But yeah, thanks. 15 is going to be the answer. Do people agree? Something else? Thank you. So it's going to be 15 here. Here's how. So this is the 1 on the right side. That's contributing 1 times to the 0. And then this one is 1 times to the first. Plus another 1, 1 times 2 squared. Plus one last one, 1 times 2 cubed. Does that make sense, how I broke that down? And if you just do the math, that's going to be 8 plus 4 plus 2 plus 1, which is a lot of addition, and that makes 15. Okay? Any questions about that? Do you see it? That's the largest 4-bit number. Makes 15. All right. So that's the one direction. That's how you go from, if I give you a binary number, how you know what it was in decimal. You can go the other way. If I give you a decimal number, like if I give you 15, can you convert it to the 1111 is the next question. There is a way to do that, and that is the harder direction. So pay extra attention to this now. So if you want to go from decimal to binary, then you have to take remainders. You have to do remainder calculations, and then also just normal division calculations. So it's division plus remainder a bunch of times. I'm so sorry. So first of all, let me introduce you to an operation. It's going to be called the percent sign, or I'm going to write it like this, but it's going to mean the modulus operation. All right. So if I give you 1, 2, 3 modulus 10, you read that as modulus or mod for short. That's an operation in math where you do the division, because it kind of looks like a division sign. You do the division and you don't give back the quotient, you give back the remainder after it's done. So this will give back, you do the division, right? What's 123 divided by 10? In like grade school math, before you learned about fractions, it was like, all right, this goes in 12 times, remainder 3, and it's the 3 that the modulus is going to get back here, right? That's a new operation. It's just like do the division and give you back the remainder, not the quotient. Does that make sense? So we're going to need that. That's going to be very, very important. And so just like this way kind of generalized from like breaking down a decimal number, let's do the same. Let's extract the digits from a decimal number. That's going to be the fancy algorithm here. So we'd like to extract the binary digits from a decimal number eventually, but let me show you the easier way. Let's extract the decimal digits from the decimal number. Let's say it's 123, because I've kind of given you the answer already. So let's say that I give you this number, and it's like in a variable or it's a black box. You can do math on it, but you don't know it yet. How can you extract like the 1, the 2, the 3, every individual digit out of this number with just mathematical operations? Do you kind of see how you might be able to use that modulus and also division? Do you see how you can get the rightmost digit with the remainder after dividing by 10? That's going to give you the 3. 123 mod 10, modulus 10, or modulo 10. That gives you back 3. You see how that's going to pick out the rightmost digit of any number? It's modulo 10 all day long. Because it's going to go in, like, give you back the other digits, remainder that last one. See it? That'll always give you the rightmost digit in your number. And then you now have a way, right? You now have a way to, like, if you give me any number, I can always give you the rightmost digit of it. Just do mod 10 on it. If I gave you, like, 234, you do mod 10, it'll give you back the 4. Mod 10 gives you back the 4. All right? Any number. Now, if only I could take my original number, my 123, and chop off the 3 that I just got out, turn it into 12. Because then I can keep playing this game. I can get the rightmost digit of 12. There's my 2. You see it? So that's what I need to do. All right? So to get the rest, I need to get this one, 123, turn it into 12, because then I can get the rightmost digit of 12, then chop off the 2, get the rightmost digit of 1. It'll all work out. All right? Do you see how the other side of this coin, of this division, gives you the rest of that number? The quotient without the remainder. There's my 12. I just chopped off the 3. I chopped off the rightmost digit by throwing away the remainder after dividing by 10. Are there any questions about that process? So dividing by 10 is powerful, in decimal at least. It chops off a digit, first of all, in the quotient, and then it gives me the rightmost digit in the remainder. That's beautiful. That's exactly what I need here. And this is like the quotient where you don't even consider the remainder anymore. It's like you chop off the 0.3 or whatever that it would have been, the 3/10. Yes? So yeah, just keep doing that. Divide by 10, throw away the remainder, and that's your algorithm. So here's an algorithm to extract all of the decimal digits of a decimal number. We'll generalize this and make it work on binary soon. But if I gave you 123, here's how you extract the 1, the 2, and the 3. You got to do it backwards. So you do mod 10, 123 mod 10. So you divide 123 by 10, give me the remainder back. It goes in 12 times with 3 left over. And there's your rightmost digit. And now you want to chop off the 3. You do 123, divide it by 10, throw away the remainder, throw away the 0.3. All right? That gives you 12. And now you just keep playing that give me the rightmost digit game. See it? So throw away the remainder when you're doing this kind of division. We call it integer division. All right, so there's that one. And now I just work with 12. Give me the rightmost digit of 12, same pattern. It goes in ones with 2 left over. There's my 2. So yeah, I can use math to pick out this stuff. And then, all right, I want to chop off the 2 from 12. How do I do it? Whatever my number was, I can always do divide by 10, throw away the remainder. That'll give me the 1 left. See it? Throwing away that. It's like not 1.2, chop off the 0.2. Give me just the 1. And then this is an algorithm, so there's a stopping condition. We're not done until it's 0. So, all right, give me the rightmost digit of 1. 1 mod 10. So if you divide it, it goes in 0 times with 1 left over. So there's my rightmost digit 1. All right, let's chop off the 1, see if there's anything left to extract. 1 divide by 10, throw away the remainder. So like the 0.1, the 0.1 goes away. So it's just 0. And that's our stopping condition for the algorithm. Do you see how every time I took a modulus, every time I did the remainder operation, I got a digit of my number in reverse order? So that's how you can extract the decimal digits of a decimal number. Are there any questions about that? So if somebody like gave you a black box, like you couldn't see what was inside, you couldn't tell that it was really 123, but you could do math on it, this is how you could figure out what the number was. Questions about this? Because this is going to generalize to extract binary digits from a decimal number, any base you care about. And do you kind of see what you're going to have to change? This is doing decimal-y stuff, isn't it? If I change that to a 2, then it's going to do binary stuff. All right? That's the secret. And so if we do that, if we change the 10s to 2s, I will be able to extract binary digits, bits, from all the numbers that I want to convert. All right, so just keep on doing it this way. Repeatedly extract the rightmost digit in binary, the rightmost bit, by doing mod 2, which makes sense, right? Because if you divide by 2, what are the remainders that you could possibly get back? 0 or 1. And then you like chop it off in binary by doing divide by 2, throw away remainders. So here, let's do an example of a very small number. Let's convert 8 to binary. 8, the number in decimal, to binary. So, all right. Here's the pattern. If I want the rightmost digit in binary of 8, I do 8 modulus 2. All right, give me the rightmost digit in binary of 8, 8 modulus 2, so you're going to divide 8 by 2 and give back the remainder. So because it's an even number, it goes in cleanly, there's nothing left over, so 0. So the 0 is the rightmost bit in binary of 8. That's kind of cool. And then I want to kind of like chop off that 0 in the binary representation of 8, and I'll do that by dividing by 2 and throwing away any remainders. There isn't any in this particular case. So 8 divided by 2 is 4, and so it's just like convert 4 to binary, tack a 0 at the end, and you're done. That's the algorithm. Okay, so now let's work on 4. 4, give me that in binary. What is 4 in binary? What's its rightmost bit? 4 mod 2. Again, it's even, so it goes in cleanly. There's nothing left over after dividing by 2. Cool. All right. So now, all right, let's chop off the 0 in binary from 4 by doing divide by 2. 4 divide by 2. Give that to me. All right. So that's going to give back 2. And again, the game is now, all right, convert 2 to binary, tack a 0 and another 0 at the end of that. I'm done. I'm getting digits out slowly but surely. I'm getting bits out. Okay. So now I'm working on 2. 2 is the number I must now convert to binary. Let's get its rightmost bit, its rightmost binary digit. 2 mod 2, still even. So it goes in once with 0 left over. And now I want to chop off that 0 in the binary representation of 2 by dividing by 2 again. All right, 2 divide by 2. Throw away remainders. 1 is left. All right, let's convert 1 to binary. Then I can put 3 zeros at the end, and I'll be done. So 1 in binary is what? Well, let's get its rightmost bit. 1 modulus 2. goes in 0 times with 1 left over. All right, let's chop off the 1 in binary from 1, see if there's anything left. 1 divided by 2, throw away the remainder, that gives me 0. So then I'm done, finally. No digits left to convert, to extract. And so every time I took a remainder, I got a digit of this number in reverse order. And so the right answer is 1000 is 8 in binary. And you can check that. This is the 2 to the zeros place, 2 to the first, 2 to the 2 squared, 2 cubed, that is 8. 1 times 2 cubed. You can always check your answer very easily. Any questions about this process? Think you can do it? All right, your turn. So here's the screenshot, and because we are shy today, let's go to the written nice page, and please write in your answer once you come up with it. I'll clear it out for us. All right, yeah. So here is a question for you, and here's the algorithm to do it. Figure out what 25 is in binary. Convert it to binary, to decimal, using this pattern. Questions about the question? So give it a try. Please collaborate with the people sitting next to you, help each other, and say hi. And get your answer in on the written nice page, please. I'll also stop attendance after this is done, so make sure to do attendance. What's 25? Remember how to check your answer. Easily check your answer. The Windows calculator can do the modulus for you. I think there's like a programmer mode that you can put it in if you want to use the big computers for help. But at least because you're dividing by 2, it's either 0.0 or 0.5, and that's how you know the remainder, right? That's my timer. Was that enough time? Let's see. Were there any questions that came up as you were trying it? You think you got it? Did you check your answer? Let's see. All right, a few of us. Nice. Let's see. Let's see if this is right. We seem to have agreed that it's 11001, those of us who submitted. So yeah, let's figure it out together. Off we go. So the process is I want the rightmost bit of 25 in binary. How do I get it? I start with 25 and I'm going to do mod 2. All right. An easy way to think of mod 2 is like it goes in cleanly if it's an even number, right? It goes in not cleanly if it's an odd number. And 25 is odd, so there's going to be 1 left over. It's going to go in 12 times with 1 left over. And so the rightmost digit of 25, rightmost bit, is going to be a 1. All right? And then, all right, let's chop off the 1 in binary from 25 by doing 25 divide by 2. Throw away the remainder. So that's going to be 12, not 0.5, just 12. Throw away that remainder. So now I'm going to convert 12 to binary, put a 1 at the end, I'm done. All right, that's my game. So what's the rightmost bit of 12? That one's even, so there's a 0 there. Chop off the 0 by doing divide by 2. Now it's 6, right? Convert 6 to binary, put a 0 and the 1 at the end of that, and I'm good. See it? So, okay, 6, what's its rightmost bit? 0. All right, give me the smaller number to now convert to binary. 3. Okay, what's the rightmost bit of 3? 3 mod 2 is 1 because it's odd. 1.5, right? 1 with 1 left over. And then, all right, chop off the 1 from 3 in the binary representation. Throw away that remainder. That's going to be 1. Yes? So now I'll convert 1 to binary, even though I know I'm done. What's the rightmost bit of 1? 1. It goes in 0 times with 1 left over. And then chop off the 1, see if there's anything left to convert. There is not. All right? And so now every time I took that modulus, I got a digit, I got a bit in reverse order. So remember that the order is in reverse. That's very important. So it looks like it's going to be 11001. Key. That reverse order is key. Okay? And that is what those of us who submitted got. Does that make sense? Are there any questions about this process? It's a little complicated, but it's going to work. And you can always check that answer, because what? This is the 2 to the 0's place, that's the 1's place, 2 squared's place is the 2's place, so the 4's place, 8's place, 16's place. So that means this is 16 plus 8 plus 1, is that correct? 24 plus 1, 25, yeah, cool. So that's an easy way to check your answer on a test, for example, right? Any questions about this? Are we happy enough? Definitely study this, good algorithm. It's a very good, very easy thing for me to ask you on the midterm, for example, all right? All right. Okay. Binary is just another number system. Let me show you that it works. You just add. You can add in the normal way. You just have to think in binary. Let me show you how. So first of all, what are these numbers? This is, or let me not even tell you what the numbers are. Let's just do the addition. All right. It works the same way you would think. So what's 1 plus 1? It's 2, right? You just have to put 2 in binary, but it doesn't work like this. There is no 2 digit. So what is 2 in binary? It's 1 0. Yeah, 1 0. So you have to carry very easily, very quickly in binary. So that's 1 0, and I have 1 plus 1 again. That's 2, which is 1 0. See it? And then 1 plus 1 plus 1 is 3, which is 1 1 in binary. And so you carry a 1 and also put a 1 down there. And again, 3, so 1 1. There's your answer. It's honestly easier. So you only have to you don't have to think of too many different digits, do you? So it's either 0 and you carry a 1 or 1 and you carry a 1. All right, so that's the answer. And you can check that answer by converting to decimal. So we know that 1111 is 15, right? That's 15. What were we really just adding? And then this one, whatever it is, it's 15 minus 2 because there's a 0 there instead. So that's 13. It's supposed to be a plus sign. So what we really just did was 13 plus 15, which is supposed to be 28. Did we do that? I think so. This is 4 plus, no, 1, 2, 4. 4 plus 8 plus 16, which should be 28. Okay? So, honestly, math is a little bit easier in binary. Could you do a binary addition? It's not horrible. Yeah, so let's come full circle, because like binary is what computers think in terms of. I taught you how to make all these fancy circuits and all these operations, and I told you that you can build a computer out of these. Let's think about this. So let's come full circle. I'll show you a circuit that adds two numbers together, in binary, of course. So this will hopefully answer this question for you, like, how in the world is my computer, like, why am I learning this in this class right now? How is my computer doing any of this? Why is binary important? Here's how, right? Here is a circuit that adds two bits together, and then you can chain it and add as many bits as you want together. So notice how exclusive OR, let's go back to the exclusive OR, it's really doing addition, isn't it? Here's exclusive OR. Because like true is a 1 and false is a 0, if you think about it. One exclusive OR with, where am I? One exclusive OR with 1 is 0. Which makes sense. That's the same as plus, right? Because you have to carry that one. The answer is really 0. See it? And then 0 plus 0 is also 0. These guys, one exclusive OR, true exclusive OR with false, false exclusive OR with true. Those are true because they're different. And that's the same as addition. Because exclusive OR is doing addition on a single bit. If you chain that, it'll work out. All right? Because then also you need to know, like, am I carrying or not? You're going to carry in the case where there were both ones, right? You have to carry the 1 in that case. And so it's just like, how do you tell if they were both ones? You AND them together. The only time they were both ones, they're both true. So that turns into a circuit. Here's an adder. Like, all right, give me 2 bits of a number. Here's their sum. This is the exclusive OR gate. It's an OR with a little slash there. There's your sum bit. And then hook into those as well. Use the AND. That'll tell me if we need to carry. There's your carry bit that feeds into the next guy. And then if you think about it, in a circuit, like if you're adding a bunch of binary numbers together, you're going to have a carry in as well as a carry out. So there's really three bits that you're adding together potentially. So this becomes a bigger circuit called a full adder that takes in 3 things: the carry in, and then your 2 bits that you're trying to add. But exclusive OR still does the job. You just chain exclusive ORs. It'll still work. All right. And it's a little bit more complicated to determine if you need to carry. It's like have a couple ands and an OR in there, but you can imagine that you could figure it out. You could draw the truth table for it. But that's it. You just take a bunch of these circuits and you feed in each of your bits in the right way. You wire them up. So like the carry in to the first adding circuit is like the carry out from the first one is the carry into the next one. It keeps on feeding down the line in that direction. But like you can chain those, and now you can add arbitrary binary numbers together and do addition inside of a computer. Isn't that amazing? I think that's really cool, and that's a big deal, right? Computers were invented to do math for us. Are there any questions about that? You'll have to wait until like a more advanced computer science class to fully understand what's going on here. But that is beautiful, and there's more where that came from. You can make any circuit to do anything. You can make circuits to move a mouse around if you wanted to. All right? So there's plenty more to discover, and I encourage you to take more CSCI classes about that. All right. If we're good, though, I have just a completely new set of slides to go to. Are you ready for it? All right. So I hope that was fun. It's fun for me to talk about. Next, I want to talk about a different topic, more philosophy again. Let's talk about privacy and encryption, because those are important terms, right? Especially on the internet. So yeah, let's talk about just like privacy first. Hopefully, we all agree that like privacy is kind of important, but privacy is a little weird in the digital space because we're on a computer, like we're connected to Canvas, we're connected to all these websites, so we have Instagram accounts or something, and we're being tracked all over the internet. We'll have to talk about that. Is that ethical? Like that's what's happening right now. It's a bit different than like nobody's like coming into your house and snooping on you, but at the same time they kind of are because they're tracking you across the internet. People are. Let's understand that. So first of all, do we even have privacy here is the first question. We do have the Constitution, right, which has the 4th Amendment, and that prohibits certain kinds of things that infringe upon your privacy. It prohibits unreasonable searches and seizures, which is nice. Like you need to get a warrant, you need to have probable cause for like somebody to come break down your door and search through your home. That is nice. We have that luxury as Americans. But the internet is not your house, is it? The internet's a different kind of place. There is no concept of you being like somewhere. Like your information is flowing out of your house, kind of through like Comcast's pipes or something. It's a completely different place. Do we have privacy there? Is the new question. You can look back to previous law on other things that leave your house. Back in the day, when phones first came out, the Supreme Court said that you don't need a warrant. The police did not need a warrant to tap your phone and listen in on your calls because, like, the line's going outside. Who cares? And also because a conversation, they determined, was not something tangible. So I can listen in on that all I want. That's what they said. That's a little unfortunate and infringing on your privacy. And they changed their minds once phones became more popular, but that was their original decision. That's interesting, right? But they didn't. The Supreme Court does have the ability, for better or for worse, to change their minds. At least it worked out then. So yeah, we have some sense of privacy, at least on phones, so maybe that applies to the internet. And now I just want to give you some examples. This is some of these are from your textbook, if you chose to get that one. So let's talk about Target. I love Target. So what Target did is they did something called data mining with their customers, and this came up a few years ago, maybe like a decade ago now, but they mined their users' data and people got upset. All right, so the word data mining is just a fancy technical term for finding patterns. It's really pattern matching. That's all it is. You got a bunch of data somehow, like Target has a bunch of your purchases. They know what you bought, how much you spent, like when you bought things. You can extract patterns out of that. It's like statistics. That's what data mining is all about, if you haven't heard that term before. So what they did, and people got a little angry about this, is it just so happens that if you're pregnant, then you buy certain products at certain stages of your pregnancy at Target, all right? And that was something that through their pattern matching they noticed, all right? People needed different things as their pregnancy was progressing, and then they took that data, they started mining it, and then they sent targeted ads, which I love that word. They sent targeted ads, Target did, and coupons to those pregnant women, all right? And people got up in arms about that. They thought that was an infringement. That was infringing their privacy, okay? So what do you think? Right? This is an ethical question right now. Is this a good thing or is it a bad thing that Target was doing this? Extracting data from people who were just shopping at Target. That's all they thought they were doing, right? Should they be given ads and coupons about things that maybe they do actually need, right? This is an ethical question, and we can ask our boys about this. Let's see what they might say. So if you asked Kant about this is a good thing or bad thing, he would ask a question like, should everyone be always doing this? Should everyone always be mining my data and extracting information and trying to sell me stuff? Kant, huge proponent of individual freedoms. He would be like, don't use me as a means to an end. He would say no, almost certainly, right? There might be a way to bend his words and have him say yes, but I would say it's very likely that you would argue no from a Kantian perspective. And then a utilitarian would be like, all right, let's weigh the options. Is there utility in this? There's two sides to that coin, isn't there? So there's the privacy side, and like the utilitarians might say, I don't like this because total utility goes down because we all lose privacy. That's an important thing. Maybe that brings the scale down in the favor of no. But you could also use utilitarianism to argue yes. You could say total utility is increased because if these pregnant women were going to buy these products anyway, and now they're getting coupons for those products, that it's cheaper for them. They're saving money. All right. So there are two sides to that coin. If I gave you an essay on this, for example, you would pick apart one of those sides, wouldn't you? All right. Are there any questions about that? So it's an ethical question. This is not the most recent thing. We've kind of all given up a lot of our data nowadays, but it's still important to talk about. All right. So just stop me if you have any questions or comments. I just have some examples right now. Next, I want to talk about ad blockers. I am a huge proponent of ad blockers. I will just tell you that right now. I hate ads on the internet. There's this thing called uBlock Origin. You can't really get it very easily on Chrome anymore, so I highly encourage you all to switch to Firefox and install this ad blocker. It will make your life so much better on the internet. But let's talk about ad blocking in general, because there's ads on the internet, and that's how websites make money. So we should talk about this. So it is not illegal to block ads, at least in the United States. But one thing that is illegal to block is ad blocker detectors on websites. So it's kind of interesting. If you go to like a news website and you have this uBlock installed, it will still notice that you have that and tell you like you should disable your ad blocker. It'll say that. it's illegal for uBlock to like try and get around that. So it's illegal to block ad blocker detectors. So you may have seen that like on Duolingo, for example. It's like buy the pro version so that you don't have to use an ad blocker instead of showing you normal ads. So the reason it's illegal to block ad blocker detectors is then that gets into a gray area with access control, which websites should have the ability to control access to who is looking at them. Because, like, for example, if you are a news website, you are publishing for all of your users like copyrighted stuff, and you want to control who gets to see that. Only the people who are like subscribers, for example, stuff like that. They only get to see that, or if you're not a subscriber, you get like 5 free views of an article or something. You probably experienced that. And so that's why ad blocker detectors are illegal. And just ad blocking in general, it's an interesting idea. So that's another ethical question. Should we be allowed to block ads? All right, even though I'm biased, let's think of this in an unbiased way and ask our boys. What would they say? This is an ethical dilemma. Let's see this. So what would Kant kind of ask if somebody asked him, like, all right, what do you think about ad blockers? Are they good or are they bad? Should we be able to use them? Should we not? Should they exist? Hmm. Yeah. Or the coupons that they were given, that's cheaper for everyone. That's exactly right. So you're a utilitarian. That's one way to think of it. Exactly. Yeah. So you give up a little privacy, but you gain maybe a lot more. That's your perspective, right? Yeah. Good thoughts. Any other ideas? Comments? Nice. So yeah, you can always frame it in these kinds of ways. There's plenty more ethical theories that you can look up, but we'll just stick to Kant and Mill in this class at least. So what would Kant say about ad blocking? He'd be like, all right, should I always be seeing ads in front of me? Should I always look at them? If I'm given one on a website, should I always be clicking them? Like that word always is very, like it hits hard here. So, okay. Then like, should I be, if I click on, am I supposed to click on all the ads? Should I be buying all the products that are offered to me? Absolutely not. Right? That's, again, being used as a means to an end. Kant would be absolutely not. I like my individual freedoms. I'm going to use an ad blocker. Probably. I think that would be what Kant would think. And then Mill, a utilitarian, would again weigh the pros and cons. So, like, what are the benefits of using an ad blocker? What do you give up? What do you lose when you use an ad blocker? So it's a pro and con list. Like a pro of using an ad blocker is, well, you've seen horrible websites. Like if I look at a news article on my phone these days, it's disgusting. Like you have to scroll over a million different ads because there's no ad blockers on iPhones, unless you do something really weird. So a pro would be like you get to actually look at your article and you're not distracted. You get more real content. All right, so that's quite nice from a lot of the users' perspectives. The flip side of that would be from the perspective of the website owners. So there's a huge con for the website owners that are trying to show you these ads that you are blocking and aren't even being downloaded. They get a lot less money. Ads are a way to make money. They make some money from just showing you the ad, a tiny amount, and then they make even more money if you click on that ad. So just by not being able to see it, you'll never click on it. So the websites are making a huge amount of less money by you blocking ads. And for smaller websites, and if that's their only source of revenue, you're going to bankrupt them maybe. And this website that you loved is now going out of business. So that's the con side to that. Okay. Does that make any sense? Any questions, comments about that? So I am biased in favor of individual rights here, but there's definitely an argument to be made. Okay. All right. Here's one last anecdote. This has changed very recently in the past year, surprisingly. This is Google Street View. It's like if you try to drag the little man out on Google Street View a year ago, this is what it looked like. It was blue everywhere that you could have the Google Street View and see all the places. But it wasn't in Germany, only the big cities. In Germany, there was no Street View. though it is a first world country, and like there was no issue getting the car to drive around and like take pictures. But Germany rejected Google Street View. Let's talk about that. For a long time, they finally gave in, but for a very, very good amount of time, several years, they thought differently than we think about this idea. So that just goes to show that different people think different things about privacy. Google Street View existed everywhere, like a year ago, everywhere in Europe, except for Germany. Except for Germany. Only the big cities. You couldn't like go see pictures of random houses and random businesses outside of like Berlin and other large cities. So what that meant is like that Germans were more interested in their privacy. They would rather have privacy than have their houses photographed and their yards and things like that. You can actually have your house blurred in Google Street View if you would like. Even in the US, you can go to them and say like, I don't want you to show my house, and they'll blur it. But like the rest of your street's still there. It's like Germany, they just didn't even allow the car to drive around, kind of. So that's very interesting to think about. That's a completely like we are similar to Germans in a lot of ways, but they really cared about their privacy in this one case in a way that we didn't. Maybe we should have been more like that. Who knows? They've given in the past year though, and Street View is a lot bigger now there. But that's what happened. That's interesting to think about, right? Not everybody has the same ideas, even though like it's still like a Western country, like we are. Cool. So yeah, with that, those are just a bunch of anecdotes. I want to talk about ways to preserve your privacy on the internet. So a big way is encryption. That's probably the main way. So we need to talk about what is encryption, how can you encrypt things, and how does that give you privacy? So, okay, the word encryption just means the idea of encoding information. Like I'm jumbling information, like I write a message and I encrypt the message and then I send the encrypted version to you, and nobody that looks in and like opens my mail can or your mail can figure out what I was saying. Only you can decode it. Right? So encryption is the process of encoding information. Only the person, it's jumbled for everyone except for you and the person who's trying to decode your message, right? So this is the metaphor. It's always like a message that needs to be sent, even if it's something on the internet. So only the people that can understand the message are the people that it's meant for, right? So only they can decode that message that you sent. And encryption is everywhere. It's used all over the place. It's used used for security, just to log in places. It's used for buying stuff, so that when you transfer your credit card information to Amazon, it's only Amazon that's seeing that, even though your data is being sent over, like if you have Xfinity, it's over Comcast's internet pipes, or if you use the school, I forget what our provider is, but like somebody, like all that is electronics being moved, and somebody can listen in on that if they wanted to. Even if they did, because of this, they won't be able to tell what your credit card number is. That's what encryption gives you. Okay, you get some very, very good guarantees. And yeah, encryption is just like this lock. See this little lock icon on your websites, even the class website, like I did that. I encrypted it for you. It's like connection secure, and you can click on it and see why. More information. You zoom in, like there's a certificate that shows you why this is encrypted. Blah blah blah. Scroll down, like, oh, there's some information here that you may be eventually be able to understand once I finish these slides today. So yeah, even the class website is encrypted. Every other website is pretty much these days. So yeah, you are securely connected to this site. Blah blah blah. Connection encrypted using TLS AES 128. Blah blah blah. Cool. Interesting. Okay. So yeah, let's talk about it. Let me show you some ideas about encryption. I'll show you, like, this is a simple encryption, then we'll get to complicated encryption that's actually used on the internet. So here we go. What is like the simplest form of encryption, a way to jumble information? The best way that I can tell you, this is an old one made in like the Roman times. It's called the Caesar cipher, or Rot 13, which is short for rotate 13. Rotate 13. And so this is an encryption scheme that is breakable. It is not like you can't encrypt anything and hope for your information to be safe. But this is like maybe 2,000 years ago, this was brand new, and everybody was like, oh, what does this mean? So this is like a form of encryption, but it's simple. It's a good one to first learn. All right. So what Rot 13 is, a Caesar cipher, it's just like take every letter of your alphabet that you're trying to send a message with and shifted over by 13. That's actually perfect because our alphabet is 16 or is 26 digits long, so 13 is just half of it. And so that makes for very nice properties. You just shift every letter of the alphabet 13 letters over. So every A becomes an N, every B becomes an O in that order, and then it just wraps back around, right? Like Z becomes an M, and M becomes a Z as well. They just wrap around, just like that. So, and then when you want to encrypt something, you just take it, like you take your hello and you look it up, add 13 digits, add 13 letters to 13 letters later in the alphabet, and so the H becomes the U, the E becomes an R, the L becomes a Y, blah, blah, blah. And so your hello turned into Uryub. Does that make sense? And that's what you send to somebody. That's encrypted now, it's jumbled, and a nice thing about the Caesar cipher is that it is its own decryption, because it's like 13 plus 13 is 26 again. Now you've wrapped it back around to the same character. So if you just do it all over again, the person on the other end just like does this all over again. Now the U becomes the H again. Now the R becomes the E again, and it'll go back and forth. So that's quite nice. So yeah, that's the Caesar cipher. That's one way to jumble information. This is not safe for anything anymore because everybody can understand it, but maybe a child would not be able to understand what you meant if you did the Caesar cipher with a message. That would be a good exercise for your kid to decrypt something, maybe. So yeah, that's one kind of encryption. Simple. Questions about this one? Because you can't hope to encrypt things on the internet with this, because anybody can just like do the thing. They know it. It's been published on Wikipedia. Here's a better one. Let's use math. There's a way to use math to get unbreakable encryption. All right, in a way that you cannot fix unless you use like a quantum computer, which nobody has invented yet. So here, it's called RSA, and this is the backbone of parts of the internet. So let me go to this website. So our class website is secured through that one. Here's some other website. Let's go to Canvas, maybe. What is Canvas secured? What's its method? They've all switched over these days. View certificate. Hey, so there it is. Algorithm, RSA. 248 size key. Interesting. So here, that was what Canvas was using to encrypt itself. I'm going to teach you RSA. All right. So it's used on the internet. And what it is, it's a kind of encryption that has like, it's a cool metaphor. It's things called keys to unlock the encryption. All right. So there's two kinds of keys in RSA. One for you to keep private, and one for you to share with everybody. All right. It's a little weird like that. So yeah, essentially there is a publicly available encryption key that you give to people who want to send you things. It's out in the open. Anybody can send you a message using this public key. So like if somebody wants to send you something using RSA, they make their message, they write it up in Microsoft Word or Google Docs, and then they encrypt it with your public key. You give that to them. And that's something that will jumble the message for you. And that will create an unbreakably encrypted text that then they send to you. This is the encrypted version. It was encrypted using your public key that you told everybody about. But this key does not unlock it anymore. It's now been jumbled in a way that cannot be unlocked with that same key. All right, that's the key. Pun intended, I guess. And so yeah, this was invented in the 70s. It just uses math to confirm and ensure that everything is unbreakably encrypted. It's so popular and so secure. If you just like use bigger and bigger numbers, that's what's involved. It's just numbers. It's still so secure that everybody uses it still. All right. And so there's this public key, and then there's also a private key that you keep for yourself. You don't share it with anybody, and that lets you decrypt the jumbled things that were encrypted with your public key. So here's kind of the setup. Here is you, and here's the person who wants to send you a message, the sender. And so you give them, if they want to send you a message, you tell them your public key. You give that to them. Out in the open, anybody can see it. And then the sender, who has your message that they want to send to you, so here it is wrapped in a nice envelope, they take your public key and they use that to encrypt this message. All right? So they take it and they encrypt it with the key. Now it's all jumbled. And then they send that encrypted, jumbled message to you using your public key that you gave to them. All right? So that's supposed to be a key. Boop, just like that. Okay? That's what happened. They gave you a jumbled thing using your public key, which you shared with everybody, but you kept a second key just for yourself. That's called a private key. These are just numbers, by the way. We'll get to it in a second. But you kept your own private key that you didn't share with anybody. And that's going to allow you to unlock this message. It undoes the public key. All right? That's the secret. And with big enough numbers and fancy enough math, you can confirm that this will work and be unbreakably encrypted. And so, yeah, what happens, the reason this works, it's going to use numbers, by the way. The reason this is so popular and still works is that it banks on the idea of factoring numbers. You've tried to factor numbers in math class before, right? It's hard even for small numbers. It takes time. It is not an easy computational process to factor huge numbers. And that's what RSA banks on. Nobody's found a good algorithm for that. We're confident that one probably doesn't even exist. And so that's why this gives us security, because it would take like a supercomputer thousands of years to unlock and guess your private key. Okay, that's it. So here's a simple example of RSA using numbers. So what you do is eventually you turn your message into a big number anyway. So this is kind of how it works. It uses what's called modular arithmetic, which is going to involve that percent sign that we were learning today. So that's perfect. We're going to use that. And yeah, here's the example. Let's say that, so here's what a public key looks like, by the way, in RSA. It's two numbers together. It's a pair of numbers, N and E, we call them, because mathematicians came up with this, of course. They just gave them single letter names. And then, so your public key is two numbers, and your private key is a third number, all right? And these all three of these numbers are generated from two giant prime numbers. That's how you confirm security, right? Just make some giant prime numbers, and it's very hard to factor things once you multiply them together, all right? So yeah, so here's example numbers that are small. You'd use much larger numbers in real life to securely encrypt things, but let's pretend that these are our numbers. This is our N, this is our D, this is our E. And D and E, by the way, they're made in kind of a similar process. You get them out together in a mathematical process. They're called modular multiplicative inverses. It's very fancy. It's very cool number theory involved here. You will learn about this if you take CSCI 26. But what I mean to say is, let's say that we have a message to send to somebody, and let's say that our message that we want to send is 42. Like we've translated our words into the number 42. And so we want to send 42 to somebody, and what's going to happen is we're going to encrypt it by like taking stuff to powers. So what I mean by modular multiplicative inverse, I'm not going to test you on this, by the way. It's just fun words to say. It's if you take m to the power of e, and then you take it to d, the power of d again, and then you do mod n on it, then it becomes equal to, not n, sorry, then it becomes equal to m again. It'll shrink it back down and become the original message. Because really it's a much huger number than m, but the second you do the modulus on it, it somehow brings it back. That's what it means to be a modular multiplicative inverse. All right? So that's the secret. That's what we're going to exploit now. So it's just some cool number theory involved here, but that's what it gives us. So yeah. Once you've picked n, that's constrained you. So you can send any message now between 0 and n minus 1, but you definitely don't want to send 0 or 1 because that would ruin the power computations, right? It would still be 1 or still be 0. So just send 2 or bigger, then you're good. And we make sure of that in the real world anyway. But now that I've said these words, let me show you how to encrypt our message to send to somebody. So they gave us their public key. Let's find the encrypted version of that message. So to encrypt the message using somebody's public key, if you want to send 42 to them, you calculate m to the power of e mod n. So that'll shrink it back down again, which is nice. So what I mean by mod is the percent sign. All right. So let's do that. Let's take m to the power of e mod n. Let's do it here. I will use Python, even though I haven't taught you Python yet. So we've got 42 to the power of, what is that, to e, which is 17. 42 to the power of 17 is that giant number. But if you shrink it back down using the modulus, mod n, which is 3233, that gives you 2557, right? So somehow shrunk that back down to a smaller number, and that we call C, 2557. And this is what you send across the internet. It's so jumbled, nobody understands it, all right? Only the person with a private key can understand it. You can't even unlock it again with your public key that you just used to encrypt it, which is perfect. And we say C here, it's called ciphertext. It's been enciphered and encrypted, right? So there's that. This is the number that you send to the person. That's your encrypted message, and they can unlock it with their private key, which is the number D, right? Because of this property, right? So to decrypt the ciphertext, you take that number to the power of D, and then you do mod n again to like shrink it back down, and magically it'll turn in to your original message M. Watch. So take the 2557, and then you calculate it to the power of D, 413, which is that number. All right, huge. And then you shrink it back down with the modulus, mod n, which is 3233, and somehow, through the magic of math, which you can learn about one day if you want to. Oh, sorry, I need to add the percent sign. 42. Oh yeah. So there it is. We get our message back, and that's how you can securely send things with big enough numbers. All right. These are too small. You can guess these easily. But with big enough numbers, that's what the internet is powered on. All right. That's how they send your credit card information, your passwords across the internet, and not get them stolen. That's RSA in a nutshell. Are there any questions about that? This is the real deal. All right. It's very cool. So let's now talk about whether this is at all ethical. Is it ethical to encrypt messages and send them to people? Because maybe that's not a good thing. Let's figure this out together. All right. So I want to have a little mini debate. So I would like you guys to get into little mini groups, and I'm going to have you, just like we did before, write in some answers, write in some ideas. All right. So I'm going to give you some numbers. I'll split you up into numbered groups, and so please go to the Written Nice page or refresh it if you're already on it, so that you can have a brand new post, because I want to clear it out. It'll mess it up if you don't refresh it. Refresh the page if you're already there. And then what I want you to do is I'm going to split you up into groups, and here's your question, right? Is it ethical to use encryption to send messages to people so that other people can't listen in? So I'll split you up into two groups. Either you're for encryption or against encryption. And so remember, what you can do is you click this button, submit, elect a leader first, click submit, and then I will give you a group number. If you are an even group number, then you are for encryption, all right? If your group is odd, then you are against encryption, okay? And so I want you to write down at least two good arguments in support of whatever stance you are, either you're for encryption or against it, and then we'll come back together and see what we think. Questions about the question? All right, take some time. I'll give you a few minutes to get together, discuss, elect a leader, and then submit at least two good arguments, please, in favor of your stance that I forced you to have, even if you don't agree with it. Another couple minutes. Make sure to get your answers in. Submit those things. Gotta click submit for me to see it. All right, one more minute. Please click submit after you've entered your stuff in. All right, that is my timer. Let's come back together. There will be more time to talk, I promise. Let's see what we're thinking. Thank you for pressing submit. Let's see what our ideas are. Some odd groups and some even groups. Let's take a look. So here's our first one is even. So even was saying we love encryption. Why is it good? Let's see. Most of the time when I want to say something, I don't want anyone to hear it. Yeah, we like privacy. That's a good argument. And when people send letters for the mail, they don't want the mail to open it and read it because it's probably private. That's the hope, right? Use a warrant if you need to. Only if this crosses international boundaries should somebody be allowed to open it. Or if the X-ray showed something weird, stuff like that. We want the same stuff for the internet. So good. And then let's look at an odd group. We don't like privacy, or we don't like encryption. Why not? Let's see. Because safety threats. People should know because maybe some bad people are conspiring to do something. We could hook into that. We could find it. For the children, right? We want to make sure that everybody's safe. Another odd group, similar ideas. Encryption can be used by criminals, and if law enforcement suddenly can't see what they're doing. That would be nice, wouldn't it? And let's do one more even group. So we like encryption because it can protect your privacy. Good. Not technically wrong. True. I would want some more explanation here, though. What do you mean by technically? An encrypted message could be used to avoid being caught doing harmful or illegal things. Yeah. Sometimes it's maybe you have to do something illegal just because of a weird gray area of the law. That's okay. All right. So that's the idea. So yeah, good thoughts. Thank you for that. Let's discuss. Let's ask our boys real quick. What would Kant think? What would Mill think? So Kant, big on personal liberties. He would probably be for privacy in general. So Kant's private. Your private info should remain private. Yeah, he'd ask that kind of question. Should I always be using encryption to send my messages? Should it always be the case that no one else can hear what I'm saying? Something like that. And yeah, he'd probably say yes. Like, yeah, I only want to be able to be heard by the people I'm talking to. That's a normal thing. Private info should remain private. I think that's what Kant might say. And then Mill, the utilitarian, would be like, what are the pros and cons? So the pro of encryption is like privacy. We love privacy. That is a nice thing to have. A con of encryption is security. So it's harder to protect people from harm, because suddenly you've allowed criminals to talk to each other in a way that you cannot break. You cannot listen in. And yeah, so that's those are the two sides to that coin. Yeah, I hope that was a fun little discussion that you guys had. I heard some good thoughts. So thank you for that. I have just one last section for the day, and I might have to skip over a slide just so that we have time to talk about your essay too. So I want to talk about three things, but probably two. You can read about the second thing. So I want to talk about some people. All right, I want to talk about Chelsea Manning first. Maybe you've heard of these people. They are famous. And they are whistleblowers. All right, they leaked stuff. So let's talk about Chelsea Manning. So in 2010, so quite a while ago, she leaked on a website that's like infamous nowadays. It's called WikiLeaks. She leaked almost 1 million classified documents, or they were unclassified but sensitive. All right, and the kinds of documents were military documents and diplomatic documents. So things that were private. All right, and that's just insane. You could not have leaked that many documents before the internet. Like, you'd have to be copying secretly 1 million things. Impossible. Right? So this is insane. What happened thanks to the internet. And so she leaked all these documents, and they were obviously classified and not meant to go out in the public. So she broke the law. She broke the law by doing this. It was absolutely not allowed to leak these documents, but she thought that it was so important to get these out to people that she broke the law anyway. Right? She was a whistleblower, and the documents had to do with, if I remember right, like civilian casualties in Afghanistan or something like that. Things that the U.S. was not talking about. And so she thought that, if people could understand what's going on really there that we're not telling them, then maybe they'll make some different voting choices or something like that. Right? So there were some cover-ups by our country that she leaked and showed that, like, no, some weird things are happening right now. You should look at them. So that was her thought process. Okay, so she broke the law, and she was sentenced to 35 years in prison for doing that. All right, but President Obama commuted the sentence, so she's free now. But she still broke the law by releasing those classified documents, even though she thought it was right. Okay, so that's our ethical question now. Does the value of, like, telling the public about potentially bad things that the government's doing or that the military is doing, does that outweigh the value of confidentiality? That is a huge question that we can ask ourselves now. All right, because there's plenty of sides to that coin. There's, on the one side, like, when you have confidentiality, when you have all these documents that are hidden away, then, like, nobody's going to try to retaliate. Confidentiality against you, because people's names were on these documents, and that was one thing that WikiLeaks did not do. They forgot to, like, scrub the names, and everybody's really mad about that. Confidentiality protects people, but luckily, like, there's no history of anybody, like, going after anybody on these documents, luckily. So that's one side of the coin. Like, that's a reason why they should stay under wraps. But on the flip side, and the reason that she made the leak was that, all right, now the second you put all this information out there for people to see, everybody gets more information. More information for people who can make choices. More information for voters, for example. Voters and activists who are against the war in Afghanistan to begin with. Now they have more firepower. Interesting, all right? So that's something to think about. It's an ethical dilemma, for sure. All right. There's another one called the Panama Papers, which I don't think I have enough time to talk about, but same idea. Some weird stuff was happening. Somebody leaked it. It was a huge leak. I encourage you to look it up. All right. The last person that I want to talk about before I get to your essay is Edward Snowden. Have we heard of that name before? He's pretty famous. He leaked documents as well a little bit later. All right. So he was working for the NSA, National Security Agency, right, for the U.S., and he leaked a bunch of documents in 2013, just showing how, like, the NSA was, first of all, the documents that he leaked were all classified. Against the law to share them, classified. And he leaked and showed that the NSA was breaking U.S. law. The NSA was absolutely breaking the law. It was spying on U.S. citizens, even though it wasn't supposed to be able to do that, right? spying on U.S. citizens and other people, and also other citizens of other countries. And it showed that we had a bunch of, we had asked companies like Facebook and stuff like that to put in back doors into their services so that law enforcement, so that the federal government can look in on it. Even though we thought that all of that information was being encrypted when we sent it to Facebook, for example, right? So there was secretly back doors up in there that nobody knew about. And so, yeah, the NSA 100% broke the law, and he leaked that fact. He leaked documents that confirmed it, right? So it was, though, against the law, of course, to leak classified documents. It was against the law to do it, and he was indicted for espionage. He had to flee the country. He is now, I think he still is, living in Russia, surprisingly. He's living in Russia with his wife because the second he goes to any country that has any ties to the U.S., he will be immediately arrested and deported back to the U.S. Okay? That's crazy. Because he did what he thought was right. Okay? So, again, that's an ethical question. Should he have done this? Should he not have done this? That's the question I'm going to ask you in your essay. All right? In your next essay. So you've got one that's not yet due, just like if you finish that one, because it's due week 4. If you finish this one early, here's your next one. So this will be due week 6. Here, I'll release it. And this is the last thing I want to tell you before we go today. So this is just a little short essay, shorter than the last one. A little 500-word essay about Edward Snowden and just like the idea of whistleblowing and the ethicalness of it in general, right? So here's your prompt. Was it correct? Was it right for Snowden to blow the whistle on the NSA? They were breaking the law. He shared a bunch of classified documents, though. He broke the law by being a whistleblower. So that's your first question. Was it right for him to do that? Your next question is, do we even have a right to privacy on the internet? It's just a public place, a public utility. We pay PG&E and they can monitor our energy as much as they want. Nobody cares. What's the difference? Tell me. Okay? That's your prompt. Does the prompt make sense? That's the main thing I want you to talk about. So I want you to respond in at least 500 words to that. And I don't care which side you're on, like I promised at the start of class. I don't care which side you're on as long as you argue well. All right? So whatever you do, you better talk about both sides of the argument. The people who love privacy, who think Snowden is great, the people who don't like Snowden, talk about both sides and how they'll pick apart the argument, and pick your side based on that, right? Either you'll bash one side and prop up another, or bash them both down. Whatever you want to do, you have to talk about both sides of the argument. The people that are for Snowden and against Snowden, right? I hope that makes sense. You don't have to talk about Kantianism or utilitarianism because I already forced you to do that, but it might be useful. I'll give you some words if you want to. And then the last thing I want to do is, even though this is only 500 words, I finally want you to cite something. All right? I want you to cite one work, at least one source in your essay. And so let's all understand, right? We know what it means to write an essay with citation requirements, right? I have sadly had to, I have to tell you, just in case you don't know, because some people have unfortunately not done this right before. So if I asked you to cite a source, in your essay somewhere, you must have either a quote or a paraphrase of your source, yes? And then you put some parentheses or whatever way you're using to cite, and then you say the source. Does that make sense? We're all aware that that's how you cite sources, yes? It's what you must do, right? What you cannot do is just say, turn in a works cited page and put a URL on it and never even mention that source in your article, in your essay, okay? Do not do that. I will give you a 0 and make you fix it. All right. So just make sure you have to cite one source, whatever you want. Could be an internet article, could be a document. You have to cite it with a parenthetical citation in your text of your essay. Okay. So sorry I have to say that. It's just your predecessors have ruined it for us. All right. So yeah, that is your requirement for your essay. And then the last thing about citations is just you can't cite Wikipedia just like every other English teacher tells you. Instead, go to the little articles that Wikipedia is citing. Go to those, read those, use those as your source. Okay, I hope that makes sense. And you can do it in any way, MLA, APA, I don't care, as long as I can understand what you're trying to say, and as long as you have an in-text citation. Okay, so yeah, I think that's all that I want to say. The due date will be week 6. You know the prompt, you know the rules. I think I've talked enough. Are there any questions about the assignment? All right. So that is all that I've got for us. You are free.